Hello, my name is John Holmes, and this is the MAE 535 project demonstration. This particular project is intended to demonstrate Faraday's law of induction, which essentially says that the change in magnetic flux with respect to time induces an EMF. The project is also capable of demonstrating a few other laws, which is Lenz's law, which essentially gives you the direction of that induced EMF. Along with the project also demonstrates some elements of magnetic circuit analysis and electrical field energy storage in a capacitor. The project is essentially a Savonius wind turbine, which is a type of vertical axis wind turbine. The Savonius design works primarily on the wind drag force and is composed of a few simple components. First component is the rotor, composed of 6 neodymium magnets oriented in a north, south, north orientation, along with blades composed from a plastic bottle and a wooden shaft, which is essentially just a wooden dowel. Next we have the stator, which is essentially 6 windings of magnetic wire, about 400 turns each, oriented in a clockwise, counterclockwise, clockwise direction. And the orientation of both the windings and the magnets will become, I'll explain in a little bit later. We also have a full bridge wave rectifier circuit, which essentially is using some germanium diodes, a ripple voltage capacitor, a bleed resistor, and an LED. Germanium diodes are used in this case due to the fact that their voltage drop is significantly less than a silicon diode. So germanium diodes exhibit maybe a quarter of a volt drop, whereas silicon diodes can reach up to half a volt. This is particularly important in low voltage applications, for solar cells, renewable energy projects. Germanium diodes are pretty typical. And of course we also have our trusty voltmeter. So first a little bit about Faraday's law of induction. Like I said, it's essentially saying that in our case, some stationary current carrying conductors in a changing magnetic field, in this case it'll be a sinusoidal magnetic field because we have a north-south orientation. So a current carrying conductors in a stationary stationary current carrying conductors in a changing magnetic field, there will be a EMF induced, and that EMF will induce some current. There will be some current because there's a load attached to it. Our load over here. And that current will be oriented in a direction given by Lenz's law, given by the right-hand rule. And that current will be oriented in such a direction such that it opposes the change in magnetic flux. So right now we don't have any flux, but as we start to wind this, turn our rotor, we'll see some change. Each one of these coils will see some change in flux, and though in each one of these there will be a current set up to oppose that change. So for example, if there's a north flux coming down this way, the right-hand rule would give current going this way, so in a counterclockwise direction for this particular coil of wire. And that's essentially Lenz's law. So first I'll demonstrate with the LED. Well, before I even go there, let me say that this design will essentially have some mechanical power, which is the wind hitting some blades. This mechanical power will be converted through the stator and rotor, through their movement. We convert it into some electrical energy, which will then go into, for my first demonstration, will go into directly to the LED. What we should see is an on-off behavior, because the output of this wind turbine will be a sinusoid, and we should see the LED turn on, off, on, off, on, off. The second demonstration will be the LED hooked up to the output of the full bridge wave rectifier circuit, and the input of the wind turbine will be hooked up to the input of the full bridge wave rectifier circuit, and we should see a more continuous, a nice on behavior of the LED, not so choppy. It won't be so choppy. It'll be more like a continuous stream of light. With that said, instead of waiting for a windy day, I'll simply simulate the wind by giving this a good turn from the hand. And we'll check, and we should get about 2.5 to 3 volts on our voltmeter. So, 3 volts, and we do see a clear on-off, on-off, on-off behavior of the LED. And that's given again by the sinusoidal waveform. As it starts to lose momentum, we get about a volt, and we don't have sufficient energy to turn on the LED. Next, we'll take the LED, hook it up to the output of our, to the input, to the output of the full bridge wave rectifier circuit. And again, we'll give it a good turn. Now this time we should see more continuous light coming from the LED, but it'll die out quicker. And that's due to the fact that we have a voltage drop among 2 diodes. Now in this case, our full bridge wave rectifier circuit is essentially turning that AC waveform into a DC waveform. And since it's a sinusoidal waveform, there will be a little bit of a ripple. This capacitor is what essentially smooths out that waveform, smooths out that ripple. And there's essentially energy being stored in this capacitor for every portion of that waveform. There'll be energy stored in this capacitor, and that's essentially just what gives us this nice smooth look if we were to hook this up to an oscilloscope. So with that said, we should see about 3 volts here, and again see a more not such a choppy movement in the LED. So the LED, about 2.8 volts, and we quickly lose the LED. We're not generating enough electricity, enough voltage to keep it turned on due to that voltage drop. With the demonstration out of the way, I would like to discuss a few of the possibilities to enhance this design, increase the efficiency, with mechanical efficiencies put off to the side. So one way would be certainly to increase the number of coils and magnets on the rotor and the stator. That would, however, translate to an increased material cost. Another way would be to increase the number of windings on each of the stator coils. So since these can be approximately solenoids, you increase the number of essentially N turns, you would get a increased current going through here. Another way would essentially be to decrease the air gap between the stator and rotor. This is again from magnetic circuit analysis. So a bigger air gap introduces certainly more reluctance, and that decreases the magnetic field strength. At this position, it decreases the magnetic field strength of those magnets on the rotor. So if you were to decrease that gap to the smallest possible amount, you'd certainly get an increased number of flux linkage between the rotor and stator. Going along those same lines, you could also put some kind of conductor or some ferromagnetic material between each of these stator windings. And that would be another way you could certainly increase the flux linkage. However, all this again translates to mainly increased cost. And that was the demonstration, and thank you very much.